So from the previous lesson on kinetic parameters and principles, you should be comfortable calculating velocity, acceleration, distance travelled and so on, and you understand what the initial and final velocity are and why we use velocity. Now this lesson takes it a stage further using more complex calculations, more complex equations, but I'll show you some methods of dealing with them to make them as easy and straightforward as possible. So let's get started. So now we're going to look at the more complex equations. Now these are often called the equations of motion or the Suvat equations, and you'll see why they're called the Suvat equations in a minute. So here we go. So the aim of the lesson is to make sure you're comfortable using these equations, rearranging them, and I'll also show you two methods of approaching these problems when you come to sit down and work them out. And there are advantages and disadvantages to each one. So first of all, the equation symbols. Now, the first one is S, and this is where you get the word Suvat from, and rather strangely, this is the letter that we use for distance. It's not D, as you might expect, it's S. You just have to remember that, but it's actually S, and obviously we measure it in meters normally for these types of problem. U we already know about, that's the initial velocity in meters per second, that's the velocity at the start of the problem, and V we know is the final velocity, the velocity at the end of the problem. A is acceleration in meters per second squared, and T logically is the time taken, and that's normally in seconds, so you need to remember if it's you're given the time in minutes or hours, you need to convert it into seconds. Now the good news about all this is the equations of linear motion, or the Suvat equations, they're all on your formula sheet. You don't need to remember them, and there are 4 of them. 2 of them we've met already, but the other 2, which look quite scary to start off with, they're not if you know how to approach them, and we'll go through that. These are on the formula sheet. So what I'd like you to do is to pause the video now and see if you can find them on your formula sheet. So here they are, and I've got them on here. This is a straight copy of the information on the formula sheet. It does say equations of linear motion with uniform acceleration. It does remind you what V, U, A, T and S all stand for, so you don't even need to remember that. And these are the 4 equations here. This one we've already met in the last lesson. This one will be new to you, as is this one as well. And this one, S equals half U plus V times T, is one we saw last lesson as well. So these 2 here are the 2 new ones. Now these can be derived from these equations by substituting one into the other and so on, but you don't need to worry about that. You won't be expected to do that in an exam. So here they are again, just to show you, make it a bit clearer. The 2 new equations that we're going to work on. And it really helps if you're comfortable rearranging equations. I will go through how you can actually do this to remind you, but if it does help if you can do this, not only for these types of problem, but for other equations as well, it's useful to be able to use these. Now the way we actually approach these problems is this, and if you stick to this method, it does make it a lot easier. So the first thing to do when you start on these problems, the first thing to do is write down the 5 letters, S, U, V, A, T. I normally put them in the top left-hand side of the paper, and what we then do is to start filling them in. So you read through the question, and you put in the ones you know, and then I always put a question mark against the one I'm trying to find out. And then what you do is look for the equation from your formula sheet of the 4 equations. Look for the one that has those 4 values in. The 3 you're given, the one you want to work out, and you ignore the other one. So let's have a go at this. Let's put this into practice. So here's a sample calculation. What is the distance travelled when a car accelerates at 4 meters per second squared from rest for 6 seconds. So, first of all, I've just put these on. You don't need to write these out on your own paper. You're given these on the formula sheet. I'm just putting them there to help us solve the problem. And write down the letters. So S, the distance, that's what you're asked to find out. So I'll put a question mark against that. U is the starting velocity. In this case, we're told it's the vehicle start, or the car starts from rest. So that's 0 meters per second squared. V, we're not given that. We're not asked to find that out. So leave that blank. The acceleration, quite clearly we're given at 4 meters per second squared. And the time it takes to do that, we're given that as well. So what we need to do now is to look at these equations over here and find an equation that has got S, U, A and T in it. So we look at the first one here. That's got V in it. We're not interested in V, so we ignore that equation. So I'll put that there, I think. Second one down here, S equals UT. We know we want to find S. We know what U is. We know what the time is. We know what the acceleration is. So this looks like it's the one to use. These other two clearly aren't any use because they've got V in them. We're not asked to find V. So this is the one you want to pick. Next thing to do is to put the numbers in that you actually know. So we know that U is 0 times time. So I'll put 0 times 6 in just to make it clear what we're doing, plus a half times the acceleration, which we're given as 4 meters per second squared, and then times the time squared, 6 squared. You then multiply that all through, and it comes out to a distance S equals 72 meters. That's how you approach these problems. And again, you want to write it out, make it really clear what you're doing, because you will get marks for your approach to the problem. It just shows you understand what you're doing. Even if you make a silly mistake at the end, you'll get most of the marks of the question if you're clearly showing the examiner what you're actually doing. And it's good practice to do that anyway. So here's a practice question for you to have a go at. Calculate the final velocity of a dragster that starts from rest and accelerates at 18 meters per second squared over a distance of 402 meters, which happens to be a quarter of a mile. So have a go at the question. So when you're ready to start, pause the video, and then afterwards I can tell you what the answer is and we can go through it if you want. Off you go. Okay, so the answer you should have got for the first question is 120.3 meters per second. If that's what you got, well done. Go on to the next section. If you're unsure about it, let's go through it. Okay, so this one here, calculate the final velocity of a dragster that starts from rest and accelerates at 18 meters per second squared over a distance of 402 meters, which happens to be a quarter of a mile, which is the normal dragster distance. So the first thing to do is to write down what you know. So the distance is 402. U we know accelerates from rest, so that is 0. V, the final velocity we're trying to find out, put a question mark there, and we're given the acceleration there. So what we need to do is to get our formula sheet here and find a formula which has got S, U, V and A in it. And first one here is no good because it's got a T in it. I've not been asked to find that, I've not been given that. Similarly, this one here is no help because again you've asked for a T there which we're not given. This one here looks more promising. Final velocity, which we want to calculate, the initial velocity, which we know, and the acceleration and the distance. So that's the one to go for. So let's write it out. V squared equals U squared plus 2AS. So put the numbers in. Now u we know is 0 because it starts from rest. So 0 plus 2 times the acceleration, which is 18, times the distance, which is 402, which gives us 14472. Remember, this is v squared, okay? That's v squared. So then to cancel out the square, you just square root both sides. So v equals the square root of 14472, which equals 120.3 meters per second. So there you go. Take it steady, do it in stages, write down what you're doing, and that should be a fairly straightforward, probably a 3-mark question, that one. So, rearranging equations. Now, you might be lucky, you might be asked to solve a problem where you don't need to rearrange the equation, but the chances are especially for the higher marks, you need to show how you can rearrange equations, not just for this topic, but for many other topics in engineering as well. So we'll look at this example here. Suppose the problem asks us to calculate the initial velocity when given the final velocity, the acceleration, and the distance. Now you can quickly use the 4 equations on the formula sheet, and you can work out the one you want is this one here, v squared equals u squared plus 2as. And what we need to do is to get u all on its own. So best thing to do is to look at this equation, and you can see that the u on its own, and with this you've got the as, that is one lump, one piece, and that's very easy to move because it's got a plus sign in front of it. All you need to do to move it to the other side of the equation is to subtract that 2as from both sides of the equation. So if you do that, you then get to this situation here. I'll rearrange it a little bit, where u squared equals v squared minus 2as. That one lump is very easy to move, that one lump of 3 things multiplied together. Now we've got u squared equals v squared minus 2as. We need to cancel out the squared, so we just need to take a square root of both sides. So u squared, the square root of u squared is obviously u, and then you put a square root symbol around the whole of this new part of the equation on the right hand side, and that will give you the correct answer. So that's one example. Here's another one, rearranging equations 2, same formula. Suppose we'd be given v, u and a and asked to calculate s, which we know is distance. There's the formula there. We can move the u squared very easily as it's one lump. So you can simply subtract that from both sides. It's quite easily done. So v squared minus u squared equals 2as. And then all you need to do is to move the 2a all on its own to the other side. We want to calculate s. These are multiplied together. So if you divide both sides by 2a, then you will cancel out and you will get s on its own. So divide both sides by 2a, and that ends up with s equals v squared minus u squared, the whole thing divided by 2a. And that's how you can rearrange equations. There will be more examples going on, and you can always go back if you're doing the exercise sheet and you're not sure. You can always go back and have a look over to get some ideas for how you go about this. Now the next slide shows an armour-piercing weapon, and this is good use of the Suvat equations. Now lots of armour-piercing weapons don't actually carry any explosive charge, and this one is an example here. This projectile is actually a hard metal dart. It can be made of a number of materials, but a hard metal dart. With this thing around here, this kind of collar, which is called the sabot, which actually prevents the exhaust gases from inside the muzzle of the gun simply blowing past the dart. That then propels the dart out of the muzzle of the gun, and it fires it with an astonishingly high muzzle velocity, the speed it exits the actual gun. and the typical values are over 1700 metres per second, which actually works out to over a mile a second. Incredibly fast. And when something that fast hits some armour plating, it can actually penetrate it amazingly, or cause damage to take out the tank. The sabot itself actually comes off after the thing leaves the weapon leaves the barrel. Those come off, and you're just left with this long, slender dart with a colossal amount of kinetic energy, which is dissipated when it actually hits the tank. So here's a sample calculation. A tank with a 6.6 metre barrel, fires an armour-piercing round with a muzzle velocity of 1,740 metres per second. And you've got to calculate the acceleration projectile as it accelerates down the barrel of the gun. So first of all, I'm just putting these on there to make it a bit easier. You say you don't need to copy these out. You can just take them straight off the formula sheet. Then I start filling it in. So I know the distance it travels is the distance along the barrel, which in this case is 6.6 metres. The initial velocity is 0. We're not told that, but we can pretty much guess that from the fact that it's a tank. It's not going to move very much at all when it's the start of the firing. The final velocity is 1740 metres per second. We've been asked to calculate the acceleration, but we don't know the time. We've not been asked the time, so we can ignore that. So we want to find an equation which has got S, U, V and A in it, but not T. And from the formula sheet here, the only one left is this one here, V squared equals U squared plus 2AS, because we know V, we know U, we know the acceleration, we're trying to find the acceleration, and we know the distance. Now in this particular case, because the initial velocity is 0, that actually drops out. So that gives us a slightly simpler equation. V squared equals 2AS. And it's the acceleration we want to calculate. So we've got to rearrange this equation. So to do that, we just need to divide both sides by 2S. That will cancel out. And that leaves A equals V squared over 2S. And we know the distance is 6.6. So we put all the numbers in. The velocity is very, very high. So we are going to get a very big number. And sure enough, we do. 229,000 metres per second squared. Incredible acceleration. And if you think about it, gravitational acceleration is 10 metres per second squared. That armour-piercing dart actually accelerates at 23,000 times more gravitational acceleration. Absolutely incredible. Amazing acceleration. So, if you're comfortable with that, let's have a look at another question for you to do. And this one here, a cyclist accelerates from 6 metres per second to 14 metres per second in 4 seconds. What is the acceleration? So try the same technique we've looked at before and see how it works. And I'll also show you another way of approaching these problems as well. So pause the video now. So the answer you should have got for the acceleration is 2 metres per second squared. If you got that, well done. Skip on to the next section. If not, we'll go through it. A cyclist accelerates from 6 metres per second to 14 metres per second in 4 seconds. What's the acceleration? So again, let's write down the SUVAT letters down the side. So we're not told the distance, we're not asked to find that, so we can ignore that. U, the starting velocity is 6. V, the final velocity is 14. The acceleration we've been asked to calculate, and the time is, we're given that as well, 4 seconds there. So we want to find an equation from our formula sheet with U, V, A and T in it. So we look at this one here. We find U, V, A and T. Actually, the first one of the 4 there fits that bill. You'll find none of the other ones can be used. That's the only one that can be used. So let's write that out. V equals U plus AT. So the next thing you need to do is to rearrange it. We've got to find the acceleration. So the first thing to do is to subtract any pieces of the equation that are either added or subtracted. So this u is obviously added, so subtract u from both sides. So you get v minus u equals at, and then we want to cancel out we want to find the acceleration. So we want to divide both sides by t, so you get acceleration equals v minus u over t, like that. So put the numbers in, and in this case we're going to be putting in 14 minus 6 divided by 4, and that comes out at 2 meters per second squared. Now if you're a bit nervous about doing all that, sometimes it's easier to do it another way. As I said before, it's better to become comfortable rearranging equations. That will help you a great deal when you do the calculus unit next year. But let's just go through it another way. So I'll put a line under here. This works just as well. So rather than rearranging the equation and putting the numbers in, you put the numbers in first. So we know what v, we know 14 equals 6 plus, in this case, a times t. We don't know that, so we just put down 4a. So I've just put the time there, 4 times the acceleration. Then it's perhaps a bit easier to see that 14 minus 6, 8 equals 4a. Then divide both sides by 4 equals 8 over 4, which equals 2 meters per second squared. Just another way of doing it. So some of the more complicated equations, you might find that an easier method to do it. Okay, here's another sample calculation, and then there'll be another question for you to have a go at. A ship accelerates at 0.05 meters per second squared in a straight line from 12 meters per second to 15 meters per second. What distance will it cover whilst it's accelerating? So again, we'll put the four formulas here. I'll put down the things we know, or things we know, and the thing we don't know, the one we're trying to find out. And we then need to find an equation with s, u, v, and a in it. And the one we can find is that has all that in is this one here: v squared equals u squared plus 2as. And what we've got to do is to work out the distance, which is the s. We want to get that on its own. So first thing we do is subtract u squared from both sides, because the u squared is one lump that's either added or subtracted to the equation. So we subtract that to the side. So v squared minus u squared equals 2as. And we're trying to find out s. So divide both sides by 2a. So v squared minus u squared divided by 2a. Put the numbers in. 15 squared minus 12 squared divided by 2 times 0.05 gives us 1810 meters, or 8.1 kilometers. So here's another question for you to have a go at. An aircraft starts its takeoff run down the runway at 4 meters per second square, 4 meters per second. It takes 25 seconds to reach takeoff velocity, covering 1.25 kilometers whilst doing so. What is its acceleration? So as normal, stop the video, have a go at this, and then restart it, and I can tell you the answer. Okay? Okay, the answer you should have got is 3.68 meters per second squared. If that's what you got, well done. Skip on to the next section, which is the end of the video. If not, I'll go through it with you. So, practice question 3. An aircraft starts its takeoff run down the runway at 4 meters per second squared. 4 meters per second, its initial velocity. It takes 25 seconds to reach the takeoff velocity, covering 1.25 kilometers. Whilst doing so, what is its acceleration? So again, we sit down, we take our time, we go through it methodically. Let's write out the SUVAT letters to the side. And then we can put the numbers in. So the distance is 1.25 kilometres. Multiply that by 1,000, 1250 metres. U is the initial speed, initial velocity, which is 4. We're not told the takeoff velocity, v, or asked to find it, so we leave that blank. We've got to find the acceleration, and we're told it takes 25 seconds. So what we've got to do is, using the formula sheet here, is to find an equation on the formula sheet which actually has all those things in it. The first one here, v, we're not asked. The first one's no use because we're not asked to find v. Second one, s, yes, we've got that. U, we know that. We know the time. And we're trying to find the acceleration. So this is the one to use here. Let's write it out. So write the equation out there, s equals ut plus half at squared, and we need to arrange it to get the acceleration on its own. Now the first thing you need to do, you've got a lump here, which is added, in this case, to the equation. You can subtract that from both sides. Okay, that looks a bit better. Then we want to get rid of these things here. So we can multiply both sides by 2. So we've got 2 minus ut. That cancels out the 2 there. At squared. And then we've just got to get the acceleration on its own. So divide both sides by t squared. So you end up with a equals 2 s minus ut over t squared, like that. All you need to do then is to put the numbers in. It's got 2,1250 minus 4 times 25 divided by squared, and that comes to 1150, because that minus that times that is 1150. 25 squared is 625, and that comes 3.68 meters per second squared. And that's the correct answer. Now some of you may be thinking, wow, that's really quite complicated to do. Well, let's do it the other way, where we put the numbers in first. So I'll draw a line down here. Okay, that's our equation here. Let's put the numbers in first. So you got 1250 equals u times t, so that's 4 times 25 minus a half a, which we don't know, and then t squared is 25 squared. I'll put a little times in there as well. So let's just multiply that through. 1250 equals 100 minus 25 squared is 625, divided by 2 is 312.5 times a, which we don't know. Then it looks a bit simpler. We can then see we can subtract 100 from both sides. So get 1150 equals minus 312.5. Oops, 5 times a. That should be plus a plus there, sorry. And then a equals 1150 divided by 312.5, which also gives us 3.68 meters per second squared. So that might be an easier way of doing it, rather than getting a bit confused by swapping things around. Put the numbers in first. That means you can simplify the look of the equation, and it just makes it a little bit easier to handle. Both of them are extremely valid. They're both, you can get full marks in the exam using both method, but this is better to use for you because it helps you later on in the course. Okay, so that's the end of these two lessons. So the main points to make on this are that you need to be methodical about it. And if you're methodical, you go through it step by step, make it clear what you're doing, you should be successful in doing these questions. There are plenty of practice questions around. Certainly, if you go through the practice questions again, the exercise questions again, maybe as revision, that will greatly help you. But remember, you can go back to the video if you want to, play back things over whilst you're doing the exercise questions to help you establish a solid method of doing this and rearranging the equations. But as you've seen, you don't have to rearrange the equations. There are slightly simpler ways of doing it, but it's a good skill to have to rearrange equations because you will meet them again next year in the calculus unit, which you have to do. So well done. See you on the next video.